Now, we can talk about how to calibrate the DAC by the chip itself. Actually, the concept is quite simple. However, if you were the first to create it, then you can file the patent, protect your innovation, and then got quite much money from all the IC companies, maybe even including Intel, Qualcomm, Broadcom, blah, blah, all of them. Yeah, this is so-called dynamically matched current sources, or simply current copying, because we would like to copy the only one reference current to all the other unit current sources. So from here, we have I reference. I need to highlight only one instead of 2 or 3. No, only one to make sure nothing will go wrong. Okay? Then how to make it? Calibration from the very beginning to the end for all the unit current sources. It means what? It will make all the unit current sources to be exactly the same with the reference in theory. But in practice, even after calibration, there will be always some kind of, again, mismatch, a little bit, but the mismatch or the error after calibration will be much, much smaller than random mismatch or systematic mismatch. In this way, we can get more than 10 bits in accuracy. The idea is quite simple. After power on, you calibrate all of them, then it means everything will become so nice and they can live happily since after, right? No. Why? Because how to calibrate such kind of current sources? Allow me to show you this way. As I mentioned moments ago, we have always done to carry some portion. This is, oh, no, sorry, this is not always done. Yeah. This is always done. Okay, and then that is for calibration or trimming. That's it. And how to hold it? Okay, after explanation, you will know what will go wrong after trimming or calibration. So for calibration, we will connect each unit current source, one by one, to the reference. And then you can see if the current is too small. Too small means the overall current here, always on and tunable transistor, right? Tunable current source, all of them, if you sum them up, the current is too small, then according to KCL, the input current will be larger than the output. What else will go to the other side, right? To charge up the capacitor here. And you can see the more voltage, the more current Q1 will conduct, right? So when it will reach equilibrium, so after the increase of Q1 current plus the fixed one equals to the reference. And again, according to KCL, no current will flow into that direction, right? No current means no change. It means this current will also be fixed. That is the end of the calibration. On the contrary, if they consume too much current, then I reference, right? What will go wrong? No, nothing, because I am larger than you. So what I can do? I will get some current, extract some current out of the capacitor, right? So the voltage will be reduced, and again, the current in Q1 will be reduced, and finally, when they are equal, congratulations, no current here means it is fixed, blah, blah, blah. So that is for calibration. And after calibration, we need real operation, right? So for normal operation, each current source will be connected to the I out or I out minus. So in reality, we don't have only two connections. Okay? Yeah, 1 power 2 stroke. No, 3. Okay? 1, 2, 3. Yeah, either for reference or for I out bar. That is, yeah, two kind of possibilities. Yeah, so you can see it looks perfect. So let's go back to this structure. After power on, in theory, we only need to do such kind of calibration. From the beginning to the end. And finally, everybody will be equal to I reference, and they can live happily since after. So I mean, the DAC will get good enough accuracy for operation, right? Right? No. Why not? Okay. The problem is here. We store the voltage on capacitor, and nothing, again, is perfect. Even for the capacitor, it needs to face leakage. Okay, not only to the capacitor, but also into the gate of Q1, blah, 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 or the switch. Okay, we need to face a lot of leakage. So it means what? After some time, the voltage here will go wrong again. So what do you need to do? Background calibration, hopefully. Okay, and that is the first issue you need to know. I mean, for any kind of creation, innovation, you need to know the pros and cons. They have some merits, but they also have some kind of demerits. You need to know all of them, then consider in which way we can further enhance it. Got it? So you can see, after calibration, you cannot stop. You need to go back again and again and again. Got it? Very similar to DRAM, right? You need to refresh. So for such kind of current copying structure, you need to make it periodically. Maybe you don't need to do it and go back immediately from the beginning to the end and then go back. No, maybe you can wait for some time, then go back to calibrate it again. And in this way, you can see during calibration, at least one of the current sources will be calibrated, right? Then the DAC cannot function, cannot work during calibration. It is harmful. Yeah, it will really like a DRAM. You have a busy signal, right? So when your end user would like you to convert something, you get, hey, sorry, I'm busy for calibration. Please wait for a while. Oh, okay, that is really troublesome, right? It doesn't make any sense. So we need to get help from the other spare part. 我没有备用电流源. One of the spare part. Okay, so you can see, for 6 bits, I told you actually we need to turn on from 0 to 63, right? So totally we only need 63 current sources, but you can see from 1 to 64. Why? Because one of them will be calibrated, and the others can carry the duty for conversion. That's it. That's it. Okay. So it means your digital circuit needs to be smart enough to know which one is calibrated, and all the others should be used for output conversion. Blah, blah, blah. Okay. So again, you can see with calibration, your layout can be much, much easier. All right. But the circuit will become much complicated. You need to pay for it. And then, to speed up the calibration, right? Oh, anyway, because we have a spare part, 我们有备用电流源哈，可以来取代被校正的那一个家伙。So it means what? Anytime. The overall DAC is functional. It is functional all the time. Never mind, you have somebody to be calibrated or not. Okay, so this is the reason why we call it background calibration, not foreground. Just like, unlike DRAM, DRAM has foreground refresh. So it needs to stop outside request during refresh. But if they can have such kind of, again, background refresh, then the DRAM can be accessed anytime. Yeah. So we wouldn't like to make any trouble for our end users to wait for us. No. They can, apply for conversion anytime as they like. They don't need to pay attention to us. So we need to have such kind of background calibration. Anyway, if you would like to have, to speed up the calibration, maybe you can have two, right? So you split them into two halves, one to calibrate the first half, the other to calibrate the second half, right? So you can double the calibration speed. Why not? Is it good? Is it good? Anybody? If you have two, right? Then you can say, hey, why don't you have 4? Oh, why don't you have 8? Oh, okay, as you like. So in this way, you can guess it is nonsense, right? If you can have 2 for reference, then you can have 4. Blah, blah, blah. Right? So what's going wrong? What's going wrong? Anybody? Okay. To be innovative. Okay. Anyway, the problem is, even though you have only 2 eye reference, how can you make sure they are exactly the same? No way. After fabrication, everybody will go wrong. Okay? So never mind how hard you try. Maybe you say, oh, I have another current reference to calibrate those 2. Forget about it. After calibration, I told you, we can make the output current as close to the reference as possible, but never be exactly the same. So if you have 1 to calibrate 2, they get some kind of mismatch, and then the 2 to calibrate the others, the error will be accumulated. It doesn't make any sense. All right? So from the very beginning till now, nobody applied more than 1 reference for calibration. No, it's a stupid idea. Don't tell me, oh, I know the limitation, then I would like to break such kind of speed limit for calibration, blah, blah, blah. That is nonsense. Okay? Don't improve it in this way. No. You will worsen the performance. Be careful. Think in advance what you can do. The other issue I need to explain is why we need to have such kind of always on current source. In theory, we can tune Q1 directly, right? It will make your life much easier than this. But why not? Briefly, if Q1 needs to carry all the current, it means what? It needs to become larger, much larger. For this one, it only carry 10%, right? To carry 100%, it means its size needs to be 10 times larger. And then this one also needs to be 10 times larger, right? It doesn't make any sense. You need to sacrifice a lot of area for this. Yeah. Anyhow, we always pursue something called good enough is the best. Too much is something we call over design. Okay? And you need to be very careful if not only you need to pay for extra chip area, but also this. If it is increased, then this switch will for all the switches, you have the so-called clock feed-through charge injection. For larger capacitance, you need to handle it harder. Okay, it is harder to handle. Blah blah blah. Okay, anyway, anyhow, it is created. Oh, see, almost 30 years ago, right? 3 decades ago. And it is reported that it can achieve, in this way, it can achieve 16-bit in accuracy. Wow. Wow. Okay. However, it needs some kind of calibration, blah, blah, blah. So in theory, it is no good for high-speed operation, but I don't buy it because the calibration is background. It's in the background instead of foreground, so it won't get any trouble for the operation. Okay, anyway, anyhow. Yeah. However, to achieve it, I still think, see, how many current sources? That is some kind of mission impossible. There are too many. All right? So you need to go back to apply this technique for what? Segmented DAC structure. MSB, apply it. LSB, maybe just like the others, let it be, or you have some way to control the ratios between MSB, I mean unit current sources, and all the others. We have, in my lab, we have, okay? But it is not published yet, so I cannot tell you the truth right now. If you are interested, just wait for our paper publication. Okay. Anyway, that is what I mentioned. Clock feed-through, charge injection. In theory, all right. For each switch, this is a very important skills. How to handle those two phenomena is a very important skill for analog IC designers, especially for SC, for switched capacitor circuit. All right. So for turning on, nothing is wrong. However, it will go wrong for turning off. During turning off, as I explained already in chapter 2, right? To refresh your mind for most operation, how to turn on? We need to how can I say? We need to get help from a lot of carriers inside the channel to make it on. All right, but after that, how to make it off? You need to expel all the charges out to make the transistor off, right? So don't expect all the charges here will go back to the left. No. Some will to the right. That is really painful. For example, if this one is MOS, right? Then the charges will be electrons. Some of them will be expelled to the capacitor. So for calibration, the voltage here is good, but after turning off, you will see some kind of voltage jump according to the charges expelled out the channel of the transistor. So how to deal with it? We say, hey, you have NMOS, then I will have the other PMOS, the so-called transmission gate, right? So you will expel some electrons, I will expel some holes to combine with each other. Perfect, right? Sorry for that. Nothing is perfect. Even during your design, it is perfect, but after fabrication, they will go wrong. So anyway, that is for charge injection, and the similar phenomenon for clock feed-through. Okay, yeah, you need to handle it. What is clock feed-through? The same. There has some kind of parasitic capacitance. So to turn it on or turn it off, yeah, some of the voltage here or there, according to voltage division, will show up here. That is really troublesome. So again, you can have both, right? to turn it on for NMOS, to turn it off for PMOS. They can cancel each other, but only in theory. In practice, not. All right, so what is the cue? What is the solution for such kind of clock feed-through and charge injection? Usually, we guess 50% of the charges will go to the output and 50 to the input. So it means what? We have, 50% of the switch to be dummy here. If you turn off, I will turn on, right? But I'm only 50% of you, so I will help you to absorb 50% of the charges you expel out perfectly. That is good. But again, nothing is perfect. How much percentage of the carriers will be pushed out from the switch? Sorry for that. It depends on many issues. For example, the impedance, look to the right and look to the left. The lower impedance will get more charges. And then the voltage. The voltage here, the voltage there. So it means what? The voltage, if the voltage here is changed, then the percentage of the charges to be expelled to the output will also be changed. It is never be fixed. So in practice, there won't be any kind of ideal value for you to design the dummy switch. Okay? Yeah, otherwise, if you Google online or search the papers through IEEE Explorer, you can find many of the papers focusing on this. They have many kind of different ideas. Anyway, anyhow, that is simplest one. 50% of the size, I mean W by L, okay, instead of over L, okay? Anyway, to absorb the charges injected to the output. Okay, that is the usual case for solution. However, you need to face the consequence. As I mentioned, the percentage of charge injection depends on many of the issues. You have no way to control it unless you have very complicated circuit to estimate the percentage, blah, blah, blah. Okay? Yeah. In theory, you can create many kind of very complicated structure, circuit to handle it, but you need to pay for it. Anyway, anyhow. Okay, that's it. Hopefully, yeah, you know the idea. Okay. Oh, finally, I explained too much. I need to speed up. What is the definition for dummy switch? It means it never be really turned on or off. Okay, so its source and drain both are connected to the output node. Got it? It doesn't help us to cut it. If you are on, I'm off. If you are off, I'm on. No, nothing will pass from the input to the output, right? So it doesn't really cut off our output 9. No, it is attached in parallel to the output 9. That's it. Keep this in mind. Okay, let's go further. That's too slow. And the other one is VTH compensation. VTH, threshold voltage compensation. Yeah, what is the problem? Oh, for this paper, to my memory, it is published by authors from NCTU, National Jiao Tong University. Or moments later, it will become National Yangming Jiao Tong University, because Yangming University and Jiao Tong University got the approval from our MOE to merge. Then it will become almost mission impossible for NTUST to defeat them. No, it will become too large. Okay, let's. The idea is, if you go back to this one, I mean, without calibration, yeah, how to make sure all the current sources are the same? Yeah, you apply exactly the same structure for all of them, right? Then how to apply bias usually we get all the biases from the so-called bias network. That is the idea, bias network. However, if you have a look at the whole chip, that is whole chip, and you have very huge area for the layout of current sources. Then you have another small area for the so-called bias network. Then route all the biases to all of them. Okay? What is the problem? The problem is the transistor here, the transistor there, according to systematic mismatch, even random mismatch, they are VTH, especially systematic mismatch, because I mentioned already for random mismatch, you can increase the transistor area to reduce it to some kind of threshold to achieve good enough performance. So to the last, you need to handle the systematic mismatch. Anyway, anyhow, the transistor here and transistor there, don't expect them will have the same threshold voltage. No, no. Here or there, here or there. No, 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 no. If they are far away, according to systematic mismatch, the threshold voltage won't be exactly the same. All right. However, you still apply, according to the traditional design, you apply all the biases from bias network. The same bias voltages for all of them, it doesn't make any sense because the current depends on this. The square of, right? Right? So even the bias is the same, but this one is different. The output current will differ a lot according to systematic mismatch. So how to handle it? In this way. Okay? That is a very good idea. You can see that is from bias network. But it is raised up by this one, compensation transistor. Yeah, and this is some kind of very small current. All right, very small current. As I told you from the very beginning in chapter 2, we have VTH plus delta V, right? And since the current here is really small, then delta V can be neglected, can be omitted. All right, so from here to there, we have 1 VTH, right? So in this way, that is from the compensation capacitor, right? So for the overall equations, it will become something like this. And this is really small, okay? Yeah, anyway, we can forget about it. Then we increase this by that. Then minus VTH. However, for each current source, the compensation transistor is laid out approximately to the current controlling transistor. Got it? They are side by side. 它们被勒得非常接近，非常近接 ，proximity. So, because they are laid out close to each other, even side by side, according to systematic mismatch, what VTH variation is faced will also be faced by MC, right? So they can cancel each other. Bingo. That is the idea from National Jiao Tong University authors and achieve better performance than before. So you can see, what is the innovation? Only this, for VTH compensation. For all the circuit, exactly the same as the traditional one. The only modification actually is this. Okay? And then the paper was accepted for publication. You can do the same thing. In analog world, innovation, creation is the king. All right? Implementation only some kind of piece of cake. Yeah, supposed to be piece of cake for everybody. Again, if you cannot make it, you can you can hire somebody to help you. Simply, you only need to submit the patent to protect your idea. Then you can even, you don't need to implement it. You can sell your IP to the other IC design houses to make big money. All right. Then, yeah, if I don't have time, I will skip to the rest. But hopefully, I will briefly, very briefly explain the idea here. Current switching sequence, as I mentioned, according to systematic mismatch, don't do anything like this. Oh, sorry, because they count the number from 1. Actually, it should be from 0. But as they like, as you like, I don't care. All right? Anyway, anyhow, moments ago, I explained again, don't do any layout like this. Continuously or sequentially to do the layout for your unit devices, it will worsen your DNL very much. You need to randomize the layout, okay? But to randomize the layout, it will become too complicated. Not only complicated, but you will get a lot of parasitics. Yeah. Anyway, anyhow, is it harmful? I mean, is the parasitic harmful for your current sources? To be honest, usually not, because current source is some kind of DC. Okay, so if you have any kind of parasitics here, parasitic there, okay, it is good to stabilize the operation. However, if you have parasitic here, then it is really harmful for your switching speed. The switching speed will be slowed down. Okay, so it depends on where the parasitics happens. Here, or there. Very good to stabilize the DC current here. But for switching, you need to pay attention to the node here. You need to reduce the parasitic capacitance as much as possible. Okay, let's go further. If you would then like to do such kind of very complicated or messy layout, 做複雜嘅啊，嗰個看嘅有個睇過嘅亂七八糟的。What you can do? We can do it in a systematic way. So that is the first I would like to share with you. Symmetric switching. What is that? 2 halves, and you can see 1, 2, 3, 4, 5, 6. Right. One to the left, the other to the right, to the left, to the right, to the left, to the right. Okay, that's it. Better than that. So what is the consequence? You can see for systematic mismatch, if it looked like this way, for original one, I mean 1, 2, 3, all the way to 16, it doesn't make any sense. Okay, but by splitting into halves, yeah, 1 and 2 and 3 and 4, right? It will look like this. Okay? Yeah, so you just count it 1 and 2 and 3 and 4. Yeah. The actual error will be reduced by 50% around. Okay? Roughly speaking. Yeah. Then you will say, hey, if I would like to go further, oh, all right. The other switching is called hierarchical switching. You can see it is split again into 2 halves, and for each half, it is further split into quarters and apply the same idea. Got it? You can see 1 and 2, then 3 and 4. Oh, sorry, the split line should be here. 3 and 4, 5 and 6, 7 and 8. Right? So, what is the outcome for such kind of hierarchical switching? Roughly speaking, the linear, if the gradient error is first order, then, got it? And then you will say, hey, if I would like to get even better performance, all right, it is only 1D, right? So, I had better to For comparison, I had better to show you from the beginning. Right, that is really bad. All right, that is nonsense for layout. And then this, I mean, without calibration or trimming. Okay. Anyway, in this way, the error will be reduced, roughly speaking, by 2, and this, roughly speaking, by 4. Okay, and then that is only 1D, 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 1D. If you would like to make it even better, so such kind of symmetrical or hierarchical switching can be applied to 2D instead of only 1D. Wow, it will make the performance even better than all of this. But again, you can see the tendency. What is the tendency? The better performance means what? The more complicated for your layout pattern. You need to pay for it. However, if you get help from EDA professors or students, you can simply show them what pattern you like. Then they can help you to finish the layout through the help of EDA tools. Just like right now on campus, we have only Professor Fang Shaoyun, Professor Shaoyun Fang in EE department. Yeah, she's the only one till now very good at EDA. For all the others, we have no idea how to control it. She and her student know how to write some script. Okay, to let EDA tools know what do you want. That's it. So we only provide the text file. Okay, the layout pattern in text file for them. Then they can help us to write the script to control the EDA and finalize all the layout for you. However, nothing is free. You need not only to get help from them, even they agree to help you after layout. I promise you, the parasitic capacitance and resistance usually will be much higher than you do it by yourself. Okay? So that is really upset. How to balance it? You need to think about it. All right? Yeah. Professor Fang told me if we have some kind of requirement, we can tell them the constraints. Okay, how to limit the resistance, the capacitance, blah blah blah. They can make it for you. Yeah. Anyhow, it will make the interface even more complicated than before. All right, that is what you need to pay if you would like to get help from EDA tools. Okay, then I would like to show you some of the, again, systematic way to achieve good enough layout. This is the so-called quad or double common centroid layout. From the beginning, for example, you have 4 bits. I mean 16 current sources to be matched. All right. What you can do from the beginning, as you like, I don't care. Okay, just like this. For each of the current sources, you can see we duplicate the layout. Vertical with vertical flipping from the left to the right, and then vertical flipping, right? That is horizontal flipping, sorry. Horizontal flipping, and then 2 of them vertical flipping. That's it. So you can see, if I'm here, then after flipping, and then, see? So we can make sure all of them, after such kind of 2 flippings, you will have the first order common centroid. Because where is my common centroid? I have 4 right now, 4 pieces. Overall, the centroid will be in the center. Got it? For all the others, the same, right? In the center. Oh, congratulations, but it only helps you achieve the first order common centroid. How to double it? You need to do it again. Okay. This one here, right? Again, flip to the right, then both of them flip down. Okay? So it means what? 1 to 4, and then to 16. Only for 4 bits. Finally, each current source is composed of 16 sub-current sources. Got it? And the pattern is here. To make sure you have good enough accuracy, you can see they have double dummy ring. Usually we have only single dummy layout, right? You can see it has double, and also, actually, for your, anyway, if your gate is here, source and drain there, right? We only need to have dummy here, dummy there, right? We don't care about the width because we have such kind of overlap. No worries. But you can see for all those very good layout, they are really cautious about etching, over etching at the boundary. So they have 2 dummy rings to make sure nothing will possibly go wrong. Okay, anyway, anyhow, it is called double common centroid or quad. All right, quad. Actually, this is quad and that is another quad. Q square, it means quad. Quad means 4, right? So 4 by 4, the square of quad means 4 by 4, 16. In theory, it is in practice, it is reported that they can achieve 12 bits in accuracy. All right? So it means what? If you would like to go for the even 1 to 16 is not good enough. Okay? You need to pay for the very complicated layout. Yeah, so that is the so-called classic. What I mentioned is the so-called classic quad switching, Q square switching. Okay, as I mentioned. So if you have, that is the first 2-dimensional first order gradient, and that is the second order gradient, right? Then you will see after distributed layout pattern, you see, wow, perfect. The first order is gone, right? Bingo. However, how about the second order? About the same. That is really upset. What we can do? You can see only the linear error is cancelled. Oh, in theory, okay? In theory, not in practice. In practice, nothing will be cancelled, but it can be reduced very much, close to 0. That is what you can expect. However, you need to make sure the size of the current control transistors should be large enough. Keep this in mind. That is your own duty, your own responsibility. Okay, that is good for the first order, but how about the second order? Sorry for that. It's no good, unchanged. All right, so how to make it? Okay, allow me to show you this. It is different from the original one. Compare to original one, see? Right? So, for the first Q, for the first quad, you can see that is original one. Flip to the right, then both of them flip downward, right? That is the original or traditional Q square switching. Then the authors of the best 14-bit stack in INL, okay, till now, it is still the best. It is called Q square random walk. You walk randomly, okay? Anyway, later I will show you how to make it. Anyway, till now, the paper is still the best for INL. Wow, it's really amazing. Nobody, no paper for decades can defeat this paper in INL. No. For linearity, the paper is still the best till now. Look into the future, I think it was still the best. Okay, it is almost mission impossible for all the other design teams. Anyway, please keep this in mind. For the original 16, I mean only for 4 bits, you need to flip to the right and flip downward, blah, blah, blah. Okay, what is changed by the authors is only one. From here, flip to the right. No, it is rotated by 180 degrees. Okay, this one is rotated. Then put here. So after rotation, it is not here but there. Got it? Got it? And then again, flip downward. So the first step is changed. From flipping to the right to rotated by 180 degrees. Got it? Then flip downward, the same. And then for the second quad, exactly the same. Okay, so there you can see, yeah, only the first step, it is rotated. Okay, instead of flipping. Then for all the others are the same. Flip downward and then flip to the right, and then all of them flip downward. Then with double dummy ring. In this way, they achieve 14-bit inaccuracy. Wow. Till now, it is still best for linearity. All right. So after some kind of estimation, no derivation at all. However, it claimed that, as you can see, for the vertical projection, 垂直投影, on the horizontal line, they have 4 points, right? Right? And how about horizontal projection to the vertical line? They have 8 projection points. So you can see, right? So they claim they can reduce. They didn't provide any derivation, only by saying. Okay, hopefully you will be convinced. Not myself. Okay, I was really curious about such kind of explanation instead of derivation. But anyway, the tendency is right. It's correct. What tendency? The more projection points, horizontally or vertically, the better performance. Okay, so they claim that with such kind of multiplication here, along x, the error will be reduced by 4, and along y, it will be reduced by 8. Okay, by 8 times. Got it? So it means what? You can change the q squared. Never mind you modify it or not. You can make it better. So for my student, the only one student from China, he helped me to modify it. Okay, for what? He helped me to swap maybe all those 3. Okay, 1, 2, 3, 4. Maybe it make it become 1, 2, 3, 4 or 3, 4. I have no idea. I forgot. Anyway, for ours, we have 8 points for both vertical projection or horizontal projection. So we claim this. All right? But after years of struggling, we have no way to implement it. It's really hard. So after asking help from Professor Huang and her student, they help us to do the final layout. But my students have some kind of regularity. Yeah, some kind of constraint according to the layout. So after they help us, the linearity is really awful. Not after fabrication, no. Even after post-simulation, after layout, from the post-simulation, the linearity is really bad. Why? Because a lot of parasitic. Not only for the resistance, but the capacitance, blah, blah, blah. Anyway, anyhow. So we have chips. We have chips. After that, after layout, after fabrication, we measure it. Oh, the INL becomes even worse. Okay. Anyway, anyhow, Professor Fang and her student said, hey, you can only make it 8 by 8, right? So they randomly choose the position by computer program to make it become 16. So they claim their performance is even better than ours. So the paper was published on the best CAT journal. Yeah, IEEE transaction on computer-aided design. That is the top 1 journal for CAT. Okay. However, they modify our concept. So they prove their concept in theory instead without any layout. No. Without any real layout. The comparison is not so good. But anyway, yeah, in her paper, she tried to compare their own layout pattern, ours, and the traditional Q-square random, just like I mentioned here. Okay, compare all those. And then the paper was published. That is unlucky for us, but it is still lucky. Unlucky or lucky is up to you, okay? Because we were also listed as the authors. Yeah, so after years, I found some of the Indians, they published another kind of paper for such kind of yeah, they didn't even achieve anything divided by 808. Yeah, according to their claim, no proof. Okay, their performance is much better. And I asked my student to simulate it, much worse than ours. So the paper actually published on transactions, IEEE transaction on VLSI systems. Because for this journal, I served as an associate editor since, to my memory, see, for so many years. I didn't pay attention to that. They don't need any kind of silicon proof. You don't need to provide the chip, the microphoto, and the measurement. No. Idea is good enough. That is really upset. If we publish our idea, then we will become the only authors for the single paper. Not only for TVSI, actually for TCAS1, the same. Okay? Only for JSSC, the top 1, it needs silicon proof. For the top 2 or the others, they don't. Idea is still good enough. So from this class, I hope you get some kind of inspiration and lesson. You learn a lesson. If you have any kind of creative idea, innovative idea, but you don't have the capability to implement it, no worries. You can submit your idea to TCAS1 or TVSI. They are still very good journals for you to publish your papers. Okay? If you have the capability to implement it, then after measurement, if it is good, you can submit your paper to the top 1, JSSC. Hopefully, yeah. Okay, we will have a short break right now, and later I will come back to show you the best in history for DAC design. I mean, according to INL, according to linearity. That is the most famous DAC design. Till now, if you would like to announce, to claim you have some kind of 14-bit DAC design, usually you need to refer, you need to cite this paper. Okay, so I hope I can help you as much as I could. Not for detailed design, no, for creativity and full understanding about the prior art. If you read the paper, I think most of you, after reading, you won't get the idea, but I can explain briefly within minutes. I hope all of you, not most of you, all of you will get full understanding about the principle for layout and then create your own. Okay?